General navigation for the DGCA exam can look like a wall of unrelated formulas, but it all comes down to a 4-step workflow. You plan your route, check your time, correct for wind, and fix any mid-air errors. Before drawing a route, you need a map. Because the Earth is an oblate spheroid, flattening it into a 2D chart requires geometric distortion. For accurate scale and measuring distances, pilots use the Lambert conformal conic projection. To draw straight run lines, we use the Mercator projection. Once you have a chart, you need a direction. In aviation, we manage 3 different norths. True north aligns with the geographic pole. Magnetic north aligns with the Earth's shifting magnetic field. And compass north is what you actually see on the direct reading magnetic compass in the cockpit. The angular differences between these 3 norths shift depending on where you are on the globe and the metal structure of your aircraft. Calculating and managing those differences is the absolute baseline of all flight planning. We manage these directional shifts using the CDMVT conversion protocol: compass, deviation, magnetic, variation, true. The standard rule of thumb moving left to right is KDET. From compass to true, add east. Let's apply this to a standard DGCA problem. We have a true track of 352 degrees, a variation of 11 degrees west, a deviation of 5 degrees west, and a drift of 10 degrees right. We need to find the compass heading. First, we find the true heading. A 10-degree right drift means the wind is blowing from the left, pushing the nose right of the track. To stay on track, we point the nose 10 degrees left into the wind. 352 minus 10 gives us a true heading of 342 degrees. Now we work backward through the sequence. Because we are moving right to left, from true to compass, we invert our math rule. We subtract east and add west. Our variation is 11 west, so we add 11 to 342, giving a magnetic heading of 353 degrees. Our deviation is 5 west, so we add 5, resulting in a final compass heading of 358 degrees. Following this exact sequence prevents the math errors that typically compromise exam scores when dealing with variation and deviation. With the direction set, we move to time. The Earth rotates 360 degrees every 24 hours. This means 15 degrees of longitude equals 1 hour of solar time, and 1 degree equals 4 minutes. We calculate local mean time by taking coordinated universal time and adding or subtracting the longitude divided by 15. Indian Standard Time simplifies this across the country. It is permanently fixed to the meridian at 82.5 degrees east. Dividing 82.5 by 15 gives us an exact offset of UTC plus 5.5 hours. The critical rule here is the direction. The Earth rotates west to east, so longitudes east of the prime meridian experience solar noon first. Because they are ahead of UTC, you must subtract the time difference to find UTC. Let's test this. If the local mean time in Delhi, at 85 degrees east, is 17:45, what is the UTC time? Take a moment to calculate it. First, convert the arc to time. 85 degrees multiplied by 4 minutes equals 340 minutes, or 5 hours and 40 minutes. Because Delhi is east, its local time is ahead. We subtract 5 hours and 40 minutes from 17:45, which gives us a UTC time of 12:05. Correctly identifying whether a location is ahead or behind UTC ensures flight plans stay synchronized across global air traffic control zones. Even with perfect planning, winds change and you drift off track. To fix mid-air errors, we use the 1 in 60 rule. This relies on the small angle approximation. For every 60 nautical miles flown, being exactly 1 nautical mile off track equals 1 degree of error. We use this to find the track error angle. You take your distance off track, divide it by your distance flown, and multiply by 60. Next, we calculate the closing angle to get back to our destination. We take that same distance off track, divide it by the distance remaining to go, and multiply by 60. Adding the track error angle to the closing angle gives you the exact heading correction you need to apply to stop drifting and fly directly to your waypoint. To avoid mid-air corrections in the first place, we use dead reckoning. This is the math done before takeoff to anticipate wind drift. Dead reckoning requires solving the triangle of velocities. We start by mapping the air vector, which represents the aircraft's intended heading and its true airspeed. Next, we map the environmental wind vector. This is the speed and direction of the air mass pushing against the aircraft. Connecting the start of the air vector to the end of the wind vector gives us our ground vector. This final line reveals our actual track over the Earth and our actual ground speed. The internal angle between where the nose points, the heading, and the physical path over the ground, the track, is our drift. Calculating this triangle lets pilots predict drift and hold a straight track through a moving air mass. These four mechanics form a unified navigation system. Here is a cheat sheet summarizing the CDMVT rule, the time conversions, the 1 in 60 formulas, and the wind triangle. Take a screenshot of this page. You can use it as your primary quick reference guide for the DGCA exam. Mastering these steps prepares you to break down and solve any general navigation problem you encounter.